In this illustration, we'll discuss about beat frequency and sound detection of three sources. Here we are given that three harmonic sources of frequency 400, 401 and 402 Hz of equal amplitude A are sounded together. And a detector receives waves directly from these three sources simultaneously. And we are given that it can detect signals only if amplitude is more than A, otherwise it remains idle. We are required to find the beat frequency registered by detector and the time for which the detector remains idle in each cycle. So here in this situation we can analyze by superposition that the three oscillations produced on a medium particle due to the three sources are, if these oscillations are represented as y1 is equals to a sine of as the value of omega here is 2 pi n, so this is 800 pi t. Y2 is equals to a sine of 802 pi t as frequency is 401, and y3 is a sine of 804 pi t as frequency is 402. So here we can write by superposition a resulting amplitude and equation of motion of medium particle. This is given by y is equals to y1 plus y2 plus y3. If we sum these three up, this gives us a multiplied by sine of 800 pi t plus sine of 802 pi t plus sine of 804 pi t. Here to add these we can add first and third, which will give us a multiplied by twice of sine of 802 pi t multiplied by cos of 2 pi t plus sine of 802 pi t. And from here we can take the sine 802 pi t common out, so this will give us a multiplied by 1 plus 2 cos of 2 pi t multiplied by sine of 802 pi t. This is what we already discussed in concept videos, that the resulting wave will again be a harmonic wave with this as an average frequency, and this factor will be the varying amplitude. So we can write this value of y as r sine of 802 pi t, which is the resulting oscillations. Here we can write this as resulting equation of motion of medium particle. And in this situation, r is the amplitude. We can write amplitude at detector is, where the waves are superposing, is given as r, which is a multiplied by 1 plus 2 cos of 2 pi t. Now in this situation, first thing we can write as r is maximum. 1 cos of 2 pi t is equals to plus 1. When cos 2 pi t is plus 1, we can write here value of 2 pi t will be 2n pi, where 2 pi gets cancelled out and the value of t we are getting is equals to n. This implies R is maximum at timings t is equals to 0, 1, 2, 3 and so on. So these are the times of maxima. That means maxima occurs after every 1 second. This will result in beat frequency which is equals to 1 by time period of maxima, that is also equals to 1 Hertz. This is one result of the term for beat frequency. We are also required to find the time for which the detector remain idle in each cycle. So here we can continue and we can write detector remain idle when R is less than equals to A. So in this situation we can equate it to A into 1 plus 2 cos of 2 pi t, and here this is giving us twice of cos 2 pi t is equal to 0. This implies the value of 2 pi t we are getting is 2n plus 1 pi by 2, then only it will be 0. This implies the value of times at which this will happen is equals to 1 by 4 second, 3 by 4 second, 5 by 4 second and so on. So at these instants the amplitude is A, and between two successive instants we can say the amplitude is more than A and then it is less than A. So if we calculate the time delta t for which detector remain idle is 0.5 seconds. So this is the time for which it remain idle. Here I am calculating simply the difference between the two timings when you can say the detector is receiving an amplitude which is more than or less than A, and all these instants are having equal time gaps. So this is the time for which it remain idle, and for the same time it will sound. So that is another result of this problem.